Okay, here's this corollary I was talking about. This is corollary 1, increasing and decreasing functions. Let f be continuous on the closed interval ab and differentiable on the open interval ab. That sounds like the mean value theorem, the CC2, and that's how we actually prove this corollary, by using the mean value theorem. But actually, it's more a statement of notation. It says if the derivative is greater than 0 at each point of the open interval, then f increases. Well, we can see that if the derivative is positive, we go back up here and we look at our situation over here. If the function is indeed increasing, you can see how the derivative or the slope is always positive. So that's all we were saying here. So they're saying if the derivative is positive at each point of the open interval, then the function increases. Now this is the tricky thing because we say it increases on the closed interval. Now sometimes it's going to be the derivative will be equal to 0 at the end point, but we'll still say that it's increasing on the closed interval as long as the derivative is positive on the open interval. So I'll show you some examples of that, so you just have to kind of remember. That's a little tricky thing on notation, because you would think when the derivative is equal to 0, if the slope is 0, that it's not increasing. So, but we just say it's increasing on that closed interval, as long as the derivative is positive on the open interval. Okay, and then looking in the other direction, if f prime is negative, that means that the slope is negative. That's an example right up here. You can see the slope is always negative. If f prime is negative at each point of the open interval, and these are just two values I picked, so this wouldn't be my open interval. I could pick any open interval. At each point of the open interval, then f decreases on the closed interval. All right, and the only thing I'm just saying is if you have a situation where our function is going like this, so we can see that, and then let's say this is point A, and this is point B, and let's say the slope is 0 at B, all right, then the function looks like it's increasing on A, from A to B, because the slope is positive until I get right here at B, that's going to come back down. So here my slope is 0, you see, so you'd say that even though the function is not greater than 0 at B, then even though f prime is greater than 0 on the open interval AB, even though it happens to be equal to 0 at B, we still say that it's increasing on the closed interval AB. So that's all I'm trying to illustrate. In other words, we might have a situation where it's increasing, and then right at B, it's 0, and then it starts decreasing. So you can say, well, it's not really increasing at B. How can I say this? Well, this is a notation thing, all right? As long as the derivative is greater than 0 on the open interval, then we say it's increasing on the closed interval. So just keep that in mind. Okay, and then let's take a look at an example. And these would be kind of like the problems you're going to be doing on homework on page 202. So rather than write down the same stipulations, you can take a look at page 202. And where it says exercises 15 through 22, they ask you to do three things, A, B, and C. And I'll just read that. It says that exercises 15 through 22 use analytical methods to find A, the local extrema, B, the intervals on which the function is increasing, and C, the intervals on which the function is decreasing. So again, we're going to use our derivatives. So first of all, I take the derivative of this, and this y prime I can call it, or f prime of x. And that's very easy to do. That's just going to be 12x minus 3x squared. And then again, we're looking for our critical values. So f prime either equals 0 or f prime is undefined, because that's where we're going to have relative extrema at those critical values. Okay. Now this is open, so there's no closed interval, so we don't have to worry about at endpoints. We're not talking about endpoints now. Okay. Well, this is a nice polynomial parabola, so it's going to not be undefined at any point, so we can just say it's not undefined, so we'll just set it equal to 0. So if we set it equal to 0, we have 12x minus 3x squared equal to 0. We'll factor out a 3x, I guess. Give me some room here, 3x. And what's left is 4 minus x equal to 0. So I've got two possibilities. Either x equals 0 or 4 minus x equals 0 or x equals 4. So those would be my two critical numbers. And we're going to do just the first derivative test because this is going to be the easiest way to deal with it. And then we'll be talking about this more in section 4.3. And so you'll know the first derivative test. So when we get to 4.3, you'll just have to deal with the second derivative test. So here's the first derivative test. So we draw a derivative line. This is going to be my f prime, or y prime, the same thing. And I'll put my critical numbers down. My critical numbers are going to be x equals 0 and x equals 4. So those are the only numbers you mark on there. Okay, and then we just want to see where it's positive or it's negative in here, so we can try some values. So let's try some values for f prime. Now, these are all values of f prime over here. And I can look at this, and this is pretty much, I can use this as a product. And remember, if the signs are the same, it's positive. If they're different, it's negative. Well, if I'm to the left of 0, I can pick any number over here. Let's say negative 1. If I put negative 1 in here, this is going to be negative. And 4 times negative 1 will be 4 plus 1. This would be positive, right? So that's just going to make this negative here. Now, I can try positive 1 over here and see what my sign is going to be here. So this would be positive, and this would be positive. So I got a positive times a positive, so that would be positive. And then over here I can try 5. And if I try 5, this is positive, but this is 4. That factor is positive because 3 times 5 is 15. And then 4 minus 5 is negative 1. That's negative, so I've got negative. Okay? So what I'll do now is I'll just mark above here what's happening. So this means basically this is decreasing here. And it's increasing here. And it's decreasing here. So this is what I want you to do because these little arrows will help you kind of indicate what's going on. So there you go. Now this is our first derivative test, really. And we're just on the A part. We're trying to find the relative extrema. And we actually have to find the values, so we could say, and then this is the formula we want to say. Well, first of all, at x equals 0, what does y equal? Because we have to find, they want you to find the local extrema. So they're looking for the values, so we need to find those values. Okay. So when x equals 0, what does f of x equal? And we have to go back to the original function. And that's up here, and that's just going to be 0, so that's nice. And then we have another one at 4 when x equals 4. I'll do that over here when x equals 4. I'll have to put that value in, and if I put that value in here, geez, it's going to be 6 times 16 minus, and then what's 4 cubed? 4 times 4 is 16 times 4 is 64. So 6 times 16, so I just put 4 in there, I just did f of 4. And that's going to be what, 96? 36, yeah. Minus 64 is going to be what? 32. Yep. So f of x or y equals 32. Okay, so that's what's happening here. So this is when x is 0, f of x is 0, and when x is 4, f of x is 32. All right? So now let's talk about A. The A part is our extrema. Letter A. And then we have the point sometimes we want just the x values, but in this case they want the point. So the point 0, 0 is a relative what? Well, 0, 0 looks like it's a relative minimum. And we're going to say because, and that's going to be f prime changes, the derivative changes from, and then you can see negative to positive there. Okay, right there. So right at that point, 0, 0. So this is the critical number. If sometimes they want just the x, and then sometimes they want the value. This is the critical value y. Okay. And then a letter. Then we also have a relative maximum. So the point 432 is a relative maximum because f prime changes. Sorry about that, changes from, that's changes, excuse me, from positive to negative. There. And again, we've got the critical number and the critical value, and there's the critical point, actually, okay? So there's our relative extrema. And then they B, they wanted the intervals in which the function is, B was in which the function is increasing, so it seems to be increasing. Now, since the derivative is, since f prime is greater than 0 on the open interval, 0, 4, then we say f, the function, is increasing. On the interval, the closed interval, 0 to 4. Okay, now you, okay, sorry about that. So since f prime is greater than 0, you can see over there the derivative is greater than 0 on the open interval because it's equal to 0 at 0 and 4. But since the f prime is greater than 0 on the open interval, we say that f is increasing on the closed interval. You don't always have to say this. You could just say that f is increasing on the closed interval. I just wanted to bring this out because that was that corollary one that we just talked about. And then letter C, when is it decreasing? Well, it's going to be decreasing. Now, infinity is always open, so negative infinity to 0, and that will be, again, closed. And from 4, and then it's going to be closed at 4, and then open to infinity. Because, again, these are the endpoints, so we give the endpoints. Even though the derivative is 0, we say that it's decreasing on this interval. So that's a little bit of a notation issue with that. Okay, so there's your A, B, and C, and that's how you would do those homework problems 15 through 22, and also 23 through 28. Okay, hope that helps.